I'm going to do a very quick introduction about the chemical naming tools that we have at ChemAxon. And so this is the agenda. First, the overview of our tools related to naming. And then I will mention just some recent improvements since last year. And then mention one of the main uses of our naming technology, which is to do document processing. So what we actually just saw was an example of that. And so I will show how that usually works. And then I will give the floor to Jeff for mentioning how they are using this technology at Linguamatics. So that's actually a graphical representation of our naming tools. I don't know if I have a pointer here. Yeah, so the idea is that, for instance, if you start from documents, one of the things you can ask is what are the chemical names in that document. And so that's the tool that we call document to structure. If you have a chemical name, you can ask what is the structure behind it, so that's name to structure. And you can also go the other way around. So given the structure as an input, what is its chemical name? Either the IUPAC name, but it could be also the common names. And so we have all these tools. And the last one is the document annotator, that given a document, will create a new document that highlights the names that are present there. So this is the family of the tools that we have in that field. So it's been tools that we have for some years now, but we keep improving them. And so I mentioned what's been happening recently. So one of the main additions last year was to add dictionaries for more fields, and so in particular for polymers, for herbicides and pesticides, and also in general a big update of the dictionary for the other fields like medicinal chemistry and general chemistry. And so in that case, we added more than 30,000 names and structures associated with them. But we also, one of the big tasks is also to respond to the customer reports about bugs and missing features or improvements that you can make. And so there were 48 of those in last year. So it keeps getting better, and it's very much driven also by the needs of our customers. Upcoming, we are really considering to add a few languages. Currently, we do English, Japanese, and Chinese. And so based on like the volume of patents and the request, that probably we will also go into German and maybe Korean. We are considering these options. And also to keep working on the dictionary, make it very easy to update it so that it can be kept up to date, and so that anytime something is released, like a new drug name is appearing, then we will very soon have it available. And then your request goes here. So we are really, as I mentioned, that very responsive, and we are really happy to know, not just guessing what people need, but actually work on the things that are useful for our customers. So this is an illustration of our document annotator tool. So you can see that as the input is these documents in various formats, and what we do is we generate a new HTML document that will highlight the names that we find. Also, it can be the images of the structures, but we use third-party tools for that. And so at the output, you have an HTML document that you can present in a web interface, for instance. And so generally, this is basically on the left side, this is the tools that I mentioned in the beginning. What's new on this picture is, if you did that, what else can you do with it? And so one of the obvious things is that once you have the structures, you can put them in a JChem database. And once you have that, then you can use, for instance, Marvin.js to draw a query, get hits from the database, and then you can visualize the results. And so that's a very typical architecture that we also work on, for instance, ChemLocator, but also several of our partners are implementing some variants of this, each of them adding their own special knowledge and added value. And so what I want to do now is to give the floor to Jeff from Linguamatics, and he will tell you more about how they use these tools at Linguamatics.
Those of you who may not be familiar with Linguamatics, we deal with natural language processing of documents, being able to extract out facts, information, and relationships from documents. We're based out of the UK. We have a US office in Boston. I am the West Coast office. I work out of my spare bedroom. We're in 18 of the top 20 pharmas, and our healthcare business has really taken off, and we're in many medical centers, cancer centers, research centers, insurers, and so forth. And we're also in government, FDA, NCI, and I'm also happy to say NASA. We recently signed a contract with them, so yeah, we do that too. The software itself, I2E, it is a graphical representation of the query, where each one of these individual boxes represents a linguistic unit that's being considered in the query, and that we generate the results in real time, unlike some open source software for text mining where you may have to recompile something or another. No, you can just modify the query, run boom, 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 one query right after the other. And it does write out a variety of file formats. What you'll see in the slides is HTML structure tables, but again, there's other file formats we can use. So I2E can be incorporated into an automatic workflow that you may have for processing your documents. There is a RESTful API that allows for the easy integration, and the reason we're here, we incorporate the ChemAxon JChem to be able to do substructure similarity searches, as well as incorporating the images in our output. To go through this, then, to give you an idea of what we can do with I2E, we'll take a little journey here where we'll start talking about web searches, and then we'll move into looking at relationship extractions, building up those relationships into something we call assertions and clustering those assertions, asking multiple questions at one time to give us then a profile or a landscape of the documents, and then finally do a join operation, what we call a join operation, where we're linking information that may be in disparate parts of the same document or across different documents. Now we'll start the journey with the web searches. We all have done web searches. We all know what Google is. And certainly they are very good at what they do, and they're making a lot of money from it. But what is a Google search? What is a web search like this? There are documents, websites, or something out there on the cloud somewhere, right? And you go in with a search engine of some sort, enter in keywords, and the magic happens behind the scenes where it searches out through the cloud or whatever, looking for where documents have those keywords. And that's what's returned to you, the documents. It's listing the documents that your hits are in here somewhere. But in order to really know what are the relevant documents, you pretty much have to go in there and look at each one of the documents. Okay, that'll get you someplace. Let's consider a little more detail, another type of Google search, a web search, in this case PubMed. And we're searching here for two drug molecules, etanercept and cyclosporin. At the time that I ran this query to make this slide, there were two hits. There were many hits, but these are the first two. And when you look inside the document, that first document's going to say etanercept and cyclosporin in very different parts of the abstract. So to be able to say that they're closely related, even though they're in the same document, maybe. The second document there, the two words are in joining sentences. Okay, the distance between them is a little bit better. You can imagine some linguistic construct that would link the two, but it's tough to say what the relationship is. And that's the thing with these document Go occurrences, that they're great at being able to find very easily that there's an association between the keywords that you have within the documents, but it's not so good at determining what is the relationship. What exactly is linking these two different keywords? Maybe a sentence co-occurrence is going to help. Well, let's take a look at a couple sentences. This first one, I'll leave it to y'all to read it. And in our mind, we look at that and we think, etanercept and cyclosporin are somewhat co-equal. There's somewhat of similar value in the treatment of whatever disease that is being discussed here. Great, we got a relationship. They're roughly the same thing. But in this sentence, etanercept demonstrates higher efficacy and good tolerability as a replacement therapy for cyclosporin. Etanercept may not be the same as cyclosporin. It might be better than cyclosporin for the treatment of plaque psoriasis. So, yeah, sentence co-occurrences, but two different types of relationships. And what we do at Linguamatics is we use natural language processing to look at the linguistics to be able to extract out more meaning, to get you into the documents in a deeper level to pick out that information that you're after. For example, consider this one. All right? First thing that we would do in our natural language processing would be identifying, well, it's not the first thing, but for the sake of the chart here. First thing is looking at entities. And it identifies, using the JChem functionality, a chemical structure. And it says, we have a chemical here. And then using an ontology later on, the entree gene ontology, we see COX-2 is in there. All right, we know that's a protein. So we've got two entities within this sentence. What's the relationship? That's where the linguistics comes in. Linguistics looks at the positions of the words and types of words and parts of speech of the words and so forth to be able to identify that one little word there, inhibitor. And that gives us then the relationship. The mesylide is an inhibitor of COX-2. And the way I said that right there, we can write it out this way. And for those of you who do the semantic web and that sort of thing, RDFs, yeah, that's a triplet. So I2E can pull out these triplets, finding this relationship between two entities. And again, one of these entities could be a chemical, which we find with JChem. All right, so we do the web searches, and I hope I convinced you that, yeah, we can go a little bit further than just keyword searches. Now let's talk about what are these relationships that we can extract. Here's one example. We're looking for biomarkers for a disease. First column gives us some proteins, genes. Second column is saying, what is the relationship? The gene is prognostic. It is an indicator. It is a marker for what's in the third column, a disease. So we're able to extract out this clear relationship that this gene, this protein can be a biomarker for the disease. We're not just telling you these documents have your hits. We are showing you the context for the hits so that you can immediately begin to do an ad hoc curation as to whether or not this query is doing what you want or what's a good hit, what's a bad hit, so forth. This is an example of a relationship we tried to find, or we worked with FDA on, where they were interested in adverse events, extracting those out of the adverse event reporting system. And what they were interested in were chemical compounds that had a benzene ring or a carboxamide group. So we used ChemAxon JChem to be able to identify those compounds that had these two chemical substructures in there. And we were able to go through the adverse event reporting database. And we were able to find 3 times the number of documents that had a specific adverse event, the Stevens-Johnson syndrome, 3 times the number that the manual curators at FDA found. So significant improvement there over what the manual inspection of the documents would do. All right, everything that I said there, all those relationships, right, those are what we call assertions. And you can have different assertions, different genes, different proteins, and so forth, all having a triplet of some sort. So what we can do is we can start stacking up these assertions into clusters. Here's another example looking at maybe some adverse events, or at least as we say here, safety issues. Notice the first column, we have the chemical. We do the JChem search on maybe a substructure search. The second column's given us then what organ in which there's been an event recognized. Third column, the dosage at which that was reported. And then the next column, certainly for that first row, it's showing that number 3 with the little blue arrow next to it. That means there were 3 documents that reported an adverse event, specifically a hard issue with this compound at 20 milligrams per mil for the dosage. I want to point you also to the hit column. Notice what's in, you might have trouble seeing it, although I have a touch of color blindness here. Whatever color that second column is, kind of a teal, bluish color. Anyway, look at the different versions of toxicity. Cardiotoxicity, toxicities, toxicity itself. If you dug further in the data, you'd be able to find like nephrotoxicity, hepatotoxicity, and so forth. All these, natural language processing was able to help us identify this is a potential problem. And then in the output, hey, thank you, ChemAxon. You gave us the chemical structures there. So the people reviewing the literature or reviewing this hit can then look at that chemical structure. All the assertions I've talked about so far, it's the same question. All right, what relationship to a protein? What's a biomarker for a protein? What dosages this drug has had a safety issue with? But we can ask multiple questions and get answers at the same time. For example, on this one, another chemical compound, but look at that second column, the different things that we're asking of the data so that we're able to find, for a given compound, a whole range of properties. What dosages was it administered? What diseases does it treat? What PK values might be associated with it? What adverse events and things like that. And you get this profile or this landscape of this chemical compound. And you get to do the same thing for documents, asking patents. I want to look for all this different information about patents and what are these different sets of patents giving me about that. And again, the chemical structure. This is another example of pointing out the chemical information where we did this for several of our customers in Europe, where recently the IDMP regulations went into play where they needed to pull out a whole host of information about their chemical compounds or drugs that they sold. And they were going to have to get this information from a myriad of places, internal documents and elsewhere. And we were able to help them develop queries and go through just tons of data, including internal documents, to be able to get the information they want. This slide is showing, I hope you can read it okay, it's for one type of document, the SMPC documents, which are roughly the equivalent of the US FDA drug labels. And in this, it gives us information such as what the drug was, what the dosage or the amount of the drug in that formulation, and other information. The last column, the one right before the hit column, is the one that I find really kind of interesting. What flavor is in the drug? What flavoring was added? And you notice it was all a refreshing peppermint flavor. Anyway, so now we can talk about getting these different facts and relationships and joining them together in different ways. One way is going through the same document, patents. All right, we just saw the talk on patents. This is another example where we're looking for exemplified compounds. And we might want to see where in that document is there some hard data about the compound, some SCR data, some inhibitory data, what have you. So what we were able to do is to go through the patents, find the exemplified compounds. Notice the IUPAC name there, which is probably not a name in any of the chemical ontologies. We got to use the ChemAxon name to structure tool to help us identify those chemical structures, plus give us the SMILE string that we can then use to go through a substructure similarity search. So now we got the example number. Now we can go in and look elsewhere within the document where that example number is referenced. In this case, it's within a table. We can look in the table elsewhere, see that it's inhibitory data. And on this particular one, the value for the example 12 is 8. And the output from I2E would give us the chemical compound, what was the the measurable that we looked at, the EC50, and that it's 8, I can't see the units there, micromolar or whatever it is, probably micromolar. So again, we're able to look elsewhere within the document, starting with the exemplified compound, and look elsewhere for every other occurrence where example 12 is being mentioned, whether it's in a table, whether it's in the text, whatever. And you can pull out that kind of quantitative information. Another case is looking between documents. Here, we're looking at two different types of queries. The first query is asking the question of a drug that has some relationship to a target. In this case, thalidomide inhibits VEGF-A on the first line there. Then we ask, of these targets, what cellular processes are they involved with? So in this case, we find the VEGF-A is related to the angiogenesis. By combining this information together, we can then say that thalidomide can have an effect on a protein that in turn affects a cellular process. And if you look over on the right, you'll notice that there are two hit columns. That's because we're finding the data in two different documents, two different Medline abstracts. So this is a means by which you might be able to repurpose old drugs or be able to identify new modes of action, mechanisms of action, and so forth, just linking data through a common factor coming from two widely different sources. So with that then, we did a little walk through the landscape here, starting from the web searches, going up through joining the documents. I gave you examples here that hopefully you agree with me are chemically relevant, because certainly we were able to do most of those with the help of the ChemAxon JChem. So with that, I will say thank you very much. And I live in San Diego, so I can stick around for any questions that you might have, okay? I'm not in a rush, although last talk of the day, I know the feeling. Thank you.